So the figure in this problem shows a string with one end attached to an oscillator and the other end passing over a pulley attached to a block. And you have four of these strings, which we're going to label A through D, set up side by side in that top view picture. And each oscillator is adjusted to vibrate the spring at a fundamental frequency, which is different for the four strings. So just to get a couple of equations out of the way, the one that you're given in this problem is the one that's not in the formula sheet, but this is the one you don't have to memorize. They will give it to you if necessary. And that is the speed of a wave on a string, which depends on the tension in the string and the linear density or mass per unit length of the string. The one that is on the formula sheet, which I'll rearrange slightly, is the speed of any wave and how it relates to wavelength and frequency. V equals wavelength times frequency. And then also we saw one of the things you derived in class was the formula for the wavelength for any harmonic. And you came up with the formula of 2L over N. And so for the first harmonic, where N is equal to 1, the fundamental frequency, the wavelength is just equal to 2 times the length of the string. So we want to know in part A what is different about the four strings that would result in their having different fundamental frequencies. So first thing is, all four strings have the same length. So according to this equation, that means all four strings are going to have the same wavelength because they're all vibrating in the fundamental frequency where n equals 1. So they all have the same wavelength, and then they have different frequencies, which means they're going to have different velocities. Since the wavelength is the same and the frequencies are different, they've got to have different velocities. So now, according to this equation, if they have different velocities, one of these two things must be different for the strings. Well, the tension is based on how much mass is hanging over the end of the string. The more mass you have on it, the higher the tension is going to be. But all four strings, it says, has the same mass hanging on it. So the only thing that could possibly be different that is not addressed in this problem is the linear density, the mass per unit length of the string. One way to think about this is it's kind of like a musical instrument that has four strings on it. The four strings will all have a different thickness. That thickness is kind of like the linear density in this problem. So that's for part A. Part B, a student graphs frequency as a function of the item determined in part A, so frequency as a function of linear density. And so what should they graph specifically so that the graph should be linear? So we're going to take this equation and for V and just plug it in over here. That way we have one single equation that relates the frequency with the linear density. So the new equation that combines these two together will be lambda f equals the square root of tension divided by linear density. So if I match this equation with y equals mx plus b, I could take on the y-axis, I could take the frequency, because that's one of the variables that's changing. And the other variable that's changing is the linear density. So on the x-axis, I could put the linear density, but notice it's under a square root sign and it's in a denominator. So I'll basically say on the x-axis, we want the square root of 1 over the linear density. And you have to put units on these as well. Frequency is really easy because we know frequency is units of hertz. But what are the units of this whole thing right here? Well, we know the linear density is mass per length. So mass per length would be kilograms per meter. Since that's in the denominator, the meters would shift up to the numerator. So it would be meters per kilogram, but it's under a square root sign, so it would be square root of meters per kilogram. If the problem actually go one step further and ask you what the slope of that graph would be, then looking back at this equation, you can see the slope is whatever's left. Don't forget, we never graphed this wavelength over here, so we'd have to first divide both sides by that wavelength. So we have like a 1 over lambda over here. So that means the slope of the graph would be equal to the square root of the tension divided by wavelength, and the wavelength is not under the square root sign. And in part C, it shows the side view of the pictures for string A, and it just says identify the second and third harmonic, and on the diagrams to mark and label all the points on the string that have the greatest average vertical speed. Well, the second and third harmonics are easy. They're just integer multiples of the first harmonic. So string A was vibrating at 400 hertz. So to get the second harmonic, you just double that number. To get the third harmonic, you just triple that number. And then on the diagram, so you remember that for the second harmonic, it looks like two loops. So from where the oscillator is down to where the pulley is, you should have one node right in the middle. That'll be at roughly the 6th line. And then just draw this really lightly on your picture because you're not actually drawing the standing wave diagram. You're gonna be marking which point has the greatest average velocity. So on your diagram, if you draw the double loop pretty lightly, where that middle dot is at the 6th line, because you have 12 lines total, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it's something like that. I think there's an extra line there. Actually, I think it's 5. Yeah, it should have 5 lines between each one. So this is like line 0. This is line 6. This is line 12. So the two places where it's oscillating with the greatest vertical speed is at the antinode. So on your diagram, you should mark the middle of this one, which is roughly about line 3, assuming we're starting at line 0, and then this one is going to be line 9. So you want to mark line 3 and line 9 on there. You want to do the same thing again for the third harmonic. So I'll let you take care of this one mostly on your own, but you're going to draw the 3 loops and make sure all the loops are equally spaced. So they should each take up about 4 lines now instead of 6 lines. And then you want to mark the antinode of each of those to show where it has the greatest average vertical speed.